last speaker before the coffee break today is Kena Chauwer from McGill University in Canada, right? Yeah. So she's going to talk about aluminum. That's right.
Sorry. Okay. Good. All right. Well, thank you for the introduction. I'm a PhD candidate in the Alternative Fuels Lab at McGill University, and it's my pleasure to be here this afternoon to talk about using aluminum as a clean energy carrier. Now, as was discussed this morning, the primary source of most of the energy that we use today is actually the sun. But when I say solar energy, most people think about things like solar concentrators and solar panels. And those sources do add a little bit to our energy mix, but it's a small fraction. And we also have wind and hydro, and these are cycles that are also driven by the sun, and they add a little bit more to the energy mix. But the major way that we're using the sun as our primary energy source today is through photosynthesis. And so that means all of the energy that we get from biomass, which includes the food that we eat, as well as the fossil fuels we're so reliant on, are really just transformed solar energy. And so although our energy system is primarily a solar energy system, we're not going about it in a very elegant way. Right now, our energy system is predicated on sort of like scrounging around in the ground and poking holes and then finding something and then burning it right away. And what we're doing is we're quite literally burning through millions of years of inherited solar wealth, and we're doing that in just a few decades, and that's what's driving climate change. In short, what we're doing is we're living beyond our means when it comes to energy. And so we need to start using our solar resources in a much smarter way. Now, of course, whenever we start talking about renewables, the first question that comes up is, do we have enough? Right now, we use about 17 terawatt of power every year. And this value is going to double in the coming decades. And about 10 years ago, some researchers at Stanford took on this question. And what they found was that we have access to about 2 terawatt of hydropower, another 40 to 80 terawatt of wind, and an overwhelming 580 terawatt of solar power. So clearly, it's not a question of supply, because we've got the supply. It's really more of a question of storage and transportation, because these forms of energy aren't always available where we want them and when we want them. So we need to figure out a way to store and to transport this energy. We need some sort of a recyclable solar fuel that we can rely on. So what are we going to use? Well, this is our menu. This is every known element in the known universe. So it has to come from here. Because the way we get energy out of anything is through some sort of a reaction, we'd want something that's readily reactive with either air or water or both. We don't want anything that's too heavy, because then the specific energy of our system is too low. We don't want anything rare, because then that's going to get expensive. And we don't want anything toxic or that becomes toxic once you react it with air or with water. We also want reasonable reaction rates, something we can control, so nothing that's too slow or too fast. And finally, we don't want our energy system competing with our food system. And because we use potassium so much for fertilizer, I go ahead and I take that off. So this is what we're left with. And it's not surprising that we see carbon up here, because that's what forms the basis of our energy system now. And a big reason that we're having such a hard time getting off of fossil fuels is because of what these fuels offer. In short, they're very energy dense, both in terms of their weight and their volume. You can have a lot of energy in a relatively small, light package. That's what these hydrocarbons offer. But we know that they're oxides, the CO and CO2, that's what's driving climate change, so we can't keep burning them. And then also, there is we're going to run out of them at some point. So we really do need to find something else. So I take this list here is what we want in our dream energy carrier, right? We want something that's energy dense, just like the hydrocarbons, but we also want something that produces no greenhouse gases anywhere in its life cycle. We want something that's safe to store and to transport. And then ideally, we also want something that's recyclable, because then we won't run into the issue of dwindling supply. So we go back to the table and we look at what's left. Well, there's hydrogen. And we've heard a lot of talk about this hydrogen economy. And hydrogen's a great fuel in terms of its specific energy, because in terms of its weight, there's a lot of energy, but not in volume. And so while we can have about 2 weeks worth of energy stored in one gas tank, so when you fill your car, that's about how much gas you have, and that's enough to run a typical North American household for about 2 weeks. To get that same amount of energy in even liquid hydrogen, you're looking at about 5 times the size. And so that's not very convenient to carry around, and it can get dangerous, because when you have a fuel that's as volatile as hydrogen, it has a very large combustion range, it can be dangerous, and it's also very difficult to store. One way to get around that would be, of course, to stabilize the hydrogen during its storage and transportation. So you can do that by taking that hydrogen molecule and then adding 3 nitrogen molecules, and then you have ammonia. And ammonia also does improve the energy density of the hydrogen, but not by much, not really enough to actually compete with the fossil fuels in terms of energy density. So we should definitely keep hydrogen in the conversation in terms of a fuel, because it is an excellent fuel. But when we're talking about storing and transporting energy, it's not really great for that. So it's not a good energy carrier. So let's go back to the table. This time we'll take hydrogen off. But right below hydrogen, there's lithium. And we're already using lithium as a fuel, right? And when we look at its energy density, it's right in there with the hydrocarbons. So it's pretty good. But we don't use lithium directly as a fuel. What we do is we make a lithium-ion battery. And because batteries have to carry around both their fuel and their oxidizer, they have very low energy densities. And so when we compare that to the hydrocarbon case, you'd actually need 45 tanks worth of lithium-ion battery to carry around the same amount of energy that you have in 1 tank of gasoline. So batteries are excellent in many applications. They're good for anything that's small and anything that's short-term, right? So our electronics, actually everything up to about a passenger vehicle, lithium-ion batteries do very, very well. But when we're talking about long-term storage, they're not so good. And then also when we're talking about any application that requires sustained high power, so really big engines, the kind of engines that we use for agriculture, growing our food, construction, any long-distance transportation, think about crossing an ocean that has no refueling stations. Lithium-ion batteries just aren't well suited for that. So we do need other alternatives for storing our energy. So let's go back to this table. I've left the lithium there for a moment. These elements all have something left in that they're all metals. And metals are very energy dense. So for example, you'd only need about half a tank's worth of aluminum to carry around the same energy that you have in 1 tank of gasoline. And when it comes to iron, it's actually about the same. And the other nice thing about these metals is that they meet our other energy carrier criteria. They're energy dense, safe to store, safe to transport, and they're recyclable. And they can potentially be made using 0 greenhouse gas emissions. So what we have here is this short list of potential clean energy carriers, right? But we have one more thing that we need to consider, and that is that we need to think about supply. So when we're talking about going to the terawatt scale with any of these, basic economics means that we have to look at the supply of any of these metals and what the demand would be, right? So these dark gray bars here show in mass how much of each of these metals would be required if for some reason we needed to take our entire energy demand for 1 year and shove it into one energy carrier. That's how much of each metal we would need. And then these light gray bars here show the known reserves in each case. There's question marks about silicon just because the quantitative estimates of silicon reserves, they're not available. But we do know that they're ample in comparison to current demand. But that doesn't really matter because, again, I'll draw your attention to aluminum and iron. And you can see that these two metals, the known reserves, can meet our energy demands many times over. In the alternative fuels lab at McGill, which is where I work, we're studying both of these as potential solar fuels, but for the rest of today, I'm really going to focus on talking about aluminum. There are two ways to use aluminum as a fuel, and the first way is what we call direct combustion, just burn it in air. There's no greenhouse gas emissions in this, there's no carbonate CO2 emissions in this mode because there's no carbon in the system. And all of the stored energy in the aluminum gets released as heat. And the second way to use aluminum as a fuel is to react it with water to form heat and hydrogen. And again, there's no CO2 emissions because there's no carbon in the system. And in this situation, what you can do is you can take the heat from the reaction and feed it directly into a heat engine. And then you can take that hydrogen and you can either burn it in air to produce more heat or feed it to a fuel cell and make electricity. And I think it's also important to notice, to comment here that this metal-water reaction using aluminum doesn't require fresh water. Seawater works very well. And then we can actually, it's very powerful. It's already been used to launch a rocket by some researchers at Purdue University. So aluminum is a fuel that we can make using renewables. Historically, electricity has been made using fuels, typically conventionals like coal and natural gas, because these conventionals were relatively inexpensive and their pricing was relatively stable. But as the price of renewables drops, it's actually beginning to make more economic sense to use electricity to make fuels rather than the status quo of using fuels to make electricity. And in 2012, the utility scale unsubsidized solar became less expensive than electricity generated using coal. And a similar crossover point happened in 2015 with combined cycle natural gas plants. So what this is an indication of is that any region that has excess renewables, excess solar, what have you, they can actually use that clean electricity to make a fuel. And we have a version of this that's already happening in Quebec, in Canada, where I live. Hydro-Quebec is our provincial utility, and they have a capacity of hydroelectric generation of 45 gigawatt. And they're also able to offer very, very competitive rates to their industrial clients. And as a result of this excess renewable and competitive rates, Quebec is the 4th largest producer of aluminum in the world, and this is despite having 0 bauxite reserves. So although the aluminum that's being made in Quebec today is not being used as a fuel, what it does show us is that if you have excess renewables and they're inexpensive, you can use those renewables to make a commodity. And then that commodity can be shipped globally. And this is the mechanism by which we can actually commodify clean energy and create a global clean energy trade system. So in such a system, the aluminum would act as the energy carrier. So wherever that clean energy is available, that's where you would process the aluminum. And when metals are processed, their energy state is increased. They're effectively storing that clean energy, and they can do so for long periods of time. So because they can do so for long periods of time without any losses, this is what would allow for that global trade, because you don't have to worry about premature discharge. The fuels can then be transported to wherever it is that they're needed, so wherever it is that you're lacking in clean energy, whether that's a temporal change, so you need to strategically store energy for seasonal variation, or if it's a geographical change, so you need to ship energy to places that are lacking in renewables. When that stored energy is needed, the aluminum is oxidized either in air or in water, and stored energy is released, and then what's left over is a solid oxide product or hydroxide. Regardless, it's an inert and it's a solid, and it does have an economic value on its own. But if we wanted to close this loop, what we can do is we can ship that back to wherever that clean energy is available and recycle it, and that's how we close the loop. So in the water oxidation mode, heat and hydrogen are the products, and that heat and hydrogen that is produced can be fed to a fuel cell, a modified diesel engine, a gas turbine engine, or it can be even used in retrofitted coal power plants to produce electricity at the grid scale. And the direct combustion cycle is exactly the same, except now air is the oxidizer rather than water. And hot gas is the product rather than heat, rather than just hot hydrogen and steam. And again, the products are fed to an engine that's appropriately sized for your application, and the oxides are collected for recycling. Now, a huge advantage of both metal water reactors and metal burners is that they're scalable. These reactors and burners can be scaled for different power needs, and in many cases, we can actually use existing equipment retrofitted to run off of the heat and hydrogen produced in the metal water reaction or the hot gas produced in the direct combustion reaction. And the reason I wanted to highlight these particular applications is because these are the types of energy applications that are currently largely still reliant on hydrocarbons. And in our research, we're showing that we do have a viable alternative to providing power at large scales using renewables, and this is a solution that is both clean and sustainable. So what's actually needed to scale to 1 terawatt by 2050? That's the key question. Well, we need an ongoing capacity to recycle about 1,000 megatons of aluminum each year. That's what we would need. And this is about 17 times the current capacity of aluminum production. So while this does seem like a lot, producing metal at this scale isn't unprecedented. We currently produce about twice this much steel every year. And so to scale to that 1,000 megatons by 2050, what we would need is a 10% increase year over year between now and then. And then we would have that target. So I do want to touch on cycle efficiency of aluminum fuel before I finish up today. Each kilogram of aluminum has energy capacity or energy content of 31 megajoule. And all of this energy can be recouped if all of the thermal energy and all of the chemical energy, if we're talking about metal-water reaction, if all of that energy is recouped. So on the first pass, this translates to a cycle efficiency of about 14%. Now, I'm assuming here that all of the embodied energy is converted to thermal energy and then fed to a heat engine, which has a thermal capacity, a thermal efficiency of about 40%, which is typical of the engines that we use now. So that's 14%. But let's keep in mind that these two costs here, both environmental, fiscal, and energetically, are only paid once, right? Because that's the step that goes from the ore that's in the ground to pure aluminum metal. So as the aluminum fuel is recycled, that cost gets amortized over several recyclings of the fuel. And then after a few cycles, we get to a cycle efficiency of about 22%. And this 22% is important because that's about where we are with natural gas combined cycle plants right now. So the last thing to mention about aluminum fuel is that even though the costs associated with the bauxite mining and the Bayer process are amortized over several recyclings, there still remains the Hall-Heroult process. And the Hall-Heroult process is how we go from aluminum oxide to aluminum. That's how we recycle it. And currently, the Hall-Heroult process uses carbon anodes in the process, which means that you're always going to have CO2. So whenever you have carbon anodes that are present, there is process CO2 emissions. But there's a new generation of anodes that are being scaled up to the industrial level as we speak. And these inert anodes completely remove the need for the carbon-based anodes in the process, and therefore are also removing any associated CO2 emissions. So now that renewable electricity is less expensive than conventional electricity, it makes sense to use the excess renewables to make fuels. And aluminum is a promising energy carrier because it's energy dense, it's plentiful, and it's soon going to be a carbon emission-free commodity. And aluminum-water reactions can be used to produce hydrogen on demand, which is a clean fuel. And then these aluminum-water reactors and the aluminum burners can be scaled for a variety of power engines, and particularly the types of engines that are still, right now, largely reliant on hydrocarbons. So I'd like to acknowledge the sponsors of this work and open the floor to any questions.
Thanks for the very nice talk. Any question from the audience? Sure.
In the recycling of the aluminum oxide, you didn't include the shipping cost to return it or to send it to where it would be used. How does that compare to the initial costs that you said we wouldn't have? Does that really affect the 22% or does it not?
We haven't done that detailed of a techno-economic assessment yet, but I will say that right now we think that it's a null because we're never sending an empty ship. So right now when we're talking about shipping coal somewhere, it's full going one way and then it's empty going the other way, or any other fuel, right? But with this type of a system, because it's completely closed loop, in one direction is aluminum fuel, gets dropped off, we fill back up with the aluminum oxide, and that goes back. So, like right now we're thinking that those cancel out, but we haven't done the formal technical assessment to see that.
Yeah, I guess I don't know how, but you still have to, like, they shouldn't cancel out because you have to pay that cost somehow for shipping. But I guess, yeah, it's forthcoming.
Other question? Sure.
Do you have any peak value for the aluminum? Because slide 22, you said it's about 31 megajoule. Is it per kilogram?
Yeah, it's 31 megajoules per kilogram.
So it is the heat value of aluminum, it's about 31 megajoule per kilogram.
I'm sorry, the which value?
Heat value.
Oh, the heating value, yeah.
And do you know, for example, it's per kilogram per liter, or for example, how much water do we need for a kilogram of aluminum?
Oh, okay. So yeah, I didn't get into the actual reaction. So per 2 mole of aluminum, depending on which reaction pathway there's a few different reaction pathways, and you'll either need 1.5 to, per 2 mole of aluminum. Yeah, so yeah, 56 kilograms. You'll either need 3, 4, or 6 moles of water.
Other question?
So any requirement on the water quality?
No. There's actually, so the research that I'm doing is using pure water, but there's other researchers who are doing work using saline solutions. So actually just adding a little bit of salt to mimic seawater, and they're actually getting better rates than with pure water.
But I'm thinking of fouling issues. So you have big tanks of water. Does it actually sort of come off the surface?
Yeah. Yeah, so that's one of the questions that we need to answer in terms of scaling this up to some sort of a commercial level, is dealing with the formalities of the reactor design. And so one of the modes that we're looking at, and I think this sort of goes to your question a little bit too, is that if this were used for, say, transoceanic transportation, then you don't have to store the water, right? Because you're on the water. And so we're hoping that that would eliminate some of those questions, but then there is an impact on the oxide product, which has to be considered. Yeah.
Great. Let's thank the speaker and all the speakers this afternoon again. And we have another 7 exciting talks after the coffee break. We restart at 3:40.